Hello, Algebra 1 students. Today we're going to be looking at the topic of linear programming. So you want to have this note guide in front of you and be filling it out as we go. You'll also probably want to take some extra notes in the margin as we go. Alright, so what is linear programming? Well, I think it's a topic that's going to tie together a lot of the inequality work that we've been doing when we've been graphing solution regions, and it's going to make that a lot more applicable to the real world. This kind of process is very involved in business and the sciences, engineering, and so forth. So what linear programming does is it's going to use multiple inequalities. So let's type that in there. So it's going to use multiple inequalities which describe like real-world limitations on a situation. In linear programming, these are usually called constraints on a situation. So the goal in linear programming is to first graph the system of inequalities, and then you're going to find the corners of the solution region. So right here in the second blank for our notes, I think we'll put corners. They're technically called vertices, so either one of those is good. So you're going to look for the edges basically of the solution region and find those vertexes at the corner, and you can do that by all kinds of different methods. You could use substitution, because remember, like the vertex of a problem, like down here on this one where we've already got the solution region graphed and all that part's done, and this vertex B at 820, you could find that 820 by doing elimination with this line and this line, or substitution with those two lines. But you're probably going to want to do it the quickest way, and I think the quickest way is to use your graphing calculator to find these corners. So let's fill this with graphing calculator. And you might even use what you're going to be using is the intersection feature that we've used so often in class. So once you've found the corners of your solution region, what you're going to do last is you're going to plug those corners into something. So you're going to have this other function. We're going to call it the target or the objective function. And it's basically what you want to maximize or minimize. And the great thing about linear programming is the maximum or minimum for your situation always has to occur at one of those corners of the solution region. So that's the neatest part about this whole thing. And I can't really prove that to you now, but you're just going to have to take it on faith. We'll look at a little bit more in that in higher level classes. Okay, so we're going to be plugging into this outside entity, this target function, in order to determine which solution in the solution region is best. And really, this whole process is the easiest type of optimization. So we're figuring out this optimal or best solution for our given set of limitations that we have to live with. For instance, a farmer has to live with they're only going to get a certain amount of rain. They've only got a certain amount of land to plant crops on. They've only got a certain amount of water that they're allotted by the water board. So those are all going to be limitations which limit what the actual answers can be. And that best solution is definitely going to occur, like I said, at one of the corners. So the objective function can kind of be anything. So let's start out with a linear objective function. So we'll say our objective function, I'm totally just making this up, is 102x minus 12y. So we've got an example where we've got everything done for us. The corners are even found already. We're just going to be plugging into the objective functions. So let's say we're going to use two different objective functions on this problem. So we've got that one, and then we've got, let me clean this up a little bit. Hold on. And then over here for our second objective function, let's make it a little more interesting. Let's make it y squared minus 2x squared. Okay, so let's plug in the different corners. So you probably want to do a little table of some sort here. Let's see if we can get a table to spawn for us. Oh, didn't want to spawn for me. So let's just type this out. So our first corner that we want to check down there is corner C. I think that's at 0.25 for this region. Then we're going to want to check corner B, which is at 820. And then we're going to want to check corner A, which looks like it is at 24.0. And we want to check the origin, because that's another corner on this region. And there we go. So let's plug each one of those into our target function f1. So we're going to do that with our calculator and go 102 times the x minus 5 times the y, and we'll get our values for each one. I'm going to do a little copy and pasting here. This one, the x was 8, the y was 20. This one, the x was 24, and the y was 0. And here we had zeros for each. Okay, so you can use your calculator or whatever. This looks like it's going to be 0 minus 5 times 25 is $1.25. So this one ends up as negative 125. Here we've got 102 times 8. I'm just going to use my calculator. That's 816 minus 5 times 20, I think, is 100. So that's 716. Let's see, this one, so we've got 102 times 24. It's going to be 2,448 from my calculator, minus 0. So, and this one's just going to be 0. So, what is the overall, not just of this solution region, all these answers in this shaded part are answers. Which one's the best in terms of the minimal value for our target, and which one's the best in terms of the maximum value? So the minimum value we got was 0, right? Like, oh wait, it wasn't 0 on this one, it was negative 125. So that could be the most important part of a problem, or it could be what went into getting that. That's more likely the important part. So what went into getting that was 0 of the x's and 25 of the y's. So that's that one. So for this objective function, the maximum that we got for the function was 716, and what went into getting that 716? And if you're saying, that's not the biggest one, 2,448 was. You're totally right. So what went into that was 24 of the x's, whatever they are, and none of the y's, whatever they are. So that's one objective function for this region. There could be a totally different objective function for this region, though. So what if we have this objective function? So I think we're going to plug in the same points. Oh, this might get interesting here. Trying to work on Microsoft Word. Let's do it. So we're going to plug in the same points. 0.25 is going to be our first one. And now we're supposed to do y squared. Okay, so 25 squared. Let's put this in an equation. So 25 squared minus 2 times x squared. 2 times 0 squared. So what's that going to be? I think it's just going to be 25 squared. So you might go to your calculator to get 25 squared, which is going to be 625. All right, there's our first one. Yeah, I'm going to use some tab action here. All right, what's our next one? So we're going to go 820, check that vertex for this new objective function. Let's see, so we're going to go 8 squared this time, minus 2 times 20 squared. You know, I really need my calculator for that. Let me pull it up here. So I've got 8 squared minus 2 times 20 squared. Negative 736. There we go. And let's see for this one. So this time we're going to check 24, 0, that third vertex. And we're going to do, so that's going to be 0 squared minus 2 times 24 squared. I'm going to go to my calculator again. So we're going to get 0 minus 2 times 24 squared. So negative 1152. Make this go over a little more. There we go. And our last one we wanted to look at was the easiest one, just the origin. So we're going to go, I think the answer is just going to be 0 here, isn't it? I mean, it's just 0 squared minus 2 times 0. I'm not going to go into the details. Okay, so for this objective function, same solution region. What's our minimum value? I think it's negative 1152, if I'm not wrong again. So this time, negative 1152 happened where? It happened with 24 units of the x and 0 units of the y. And the maximum we could get for this objective function was 625, and that happened at 0.25. So for this region, the 24, 0a and 0.25, c, those are our popular points, if you will. Okay. We'll go and look at a full-blown application where we do everything, and then at the very end use our objective function now. Alright, so let's look at a fully blown example of linear programming. And by full blown, I don't mean that this will cover like all the little intricacies that you would need to solve an optimization problem like this in the real world, but it's pretty darn close actually. So we've got this company. I won't talk long about their name. I thought it was a little more intriguing than things I'd seen like Wonder Bats. Anyway, so this company's manufacturing 2 different kinds of baseball bats. They've got a wood one, and they've got some kind of secret polymer one. Something you can imagine it being metal if you like. So anyway, the wood bat takes 8 hours to trim on a lathe, and it takes 2 hours to finish to make it nice and polished, and to put all the right kinds of things on the outside of the bat so that it hits baseballs correctly. The polymer bat takes a little longer to trim, or excuse me, a little less time to trim. For whatever reason, their metal polymer lathe must work better. But it takes a lot longer to apply those sealants. It's got all kinds of different things you've got to put on it before it's ready to go. So the total amount of lathe time that this little mom and pop baseball shop has available for these bats is 80 hours. That's based on the number of employees they have and everything. And the total amount of finishing room time they have is only 50 hours, and that has to do with their employees that can only be exposed to these kinds of harsh fumes for a certain amount of time every week for their health or whatever. Pretty realistic to the real world. So first, you always want to begin by choosing variables clearly. So what are the things that are changing in the situation? What are the things that you, as the bat company, have control over in terms of the manufacturing process? Well, I think that you have control over how many wood bats you're shooting for, and you have control over how many polymer bats that you try to make in a week. This looks like it's just 1 week, yeah. Anyway, so I said there were 4 different inequalities, and of course in a real situation you're not going to be told that. You've just got to write down an inequality for each constraint. So in this box here I tried to make a hint. So when you're working on your own problems, you always want to start the problem by thinking about what aspects limit the situation. They could be things like money, they could be things like the amount of bats you have, they could be things like you only have a certain amount of man-hours in order to produce cars. I think there's one like that on yours. They could be you only have a certain amount of fuel in order to launch the rocket into orbit. So if you start by trying to label what the problem is about, it's going to be so much more helpful. So try to figure that out first. What are the 2 features of our situation that we have limiting us in this situation? So you can label it however you want. It's not like there's a right and a wrong answer. This is just to guide you. So I think that one of the ones we have is lathe time for us. That's what makes sense to me. So we've got the lathe time, and then we've got the finishing or polishing or whatever it is that goes into that finishing time for each kind of bat. Okay, so there's no reason why I have a bunch of boxes here. It's just I tried to make this bracket thing big enough. So there's only supposed to be 4. So the first one, what are we going to do? So lathe time. What's the information about lathe time? Try to go pick it out and get it all by itself. So we had 8 hours for the wood bats. And wood bats we called x, so let's say 8x. And then we're also going to need some lathe time, so I'm going to say plus. How much lathe time did the polymer bats take? I think they were 5 hours for each one. So that's the amount for each wood, that's the amount for each polymer. And then how many hours did we have on the lathe? I think we only had 80, so stick an 80 in there. And then think about it. What's the symbol going to be in here? We had it, right? So it's going to be equal to. Is it less than or more than 80? Well, 80 is the top, so I think it's going to be less than or equal to. So there's the lathe time one. Now let's look at finishing time. The wood bats had 2 hours each. The polymer bats had, I think, 5 hours for their sealants, whatever they were. Now, there's different kinds of stuff going on these bats, but this is total time that's spent in the finishing room. And we're only supposed to have 50, so I think that's got to be less than or equal to 50. All right, so are there any other constraints or limits on our situation? So I don't think there are from this information. There probably is in reality, but there's a couple that aren't even described in here. And I think that has to do with, for the graph over here that I set up for you, it's only in the first quadrant. Why is it only in the first quadrant? Think about it for a second. My class quickly told me that it was only in the first quadrant because you can't have negative baseball bats. So over here, let's add on another thing that says no negative, make this a little bigger, no negative bats of either kind. So we need 2 more constraints really that say you can't have negative bats. In other words, x has to be greater than or equal to 0, and y has to be greater than or equal to 0. So there's the 4 constraints on this situation. Now you want to graph them. So let's go ahead and graph them. I'm going to scoot these guys over a little bit. Alright, so let's go ahead and graph these. So we're going to have to solve for y on each one first. So this is going to be y is less than or equal to, and I'm going to just solve for y. We've done this lots of times in class. I think it's going to be negative 8 divided by 5x plus 16. So if you solve for y on that, that's what you'll get. And on this one, be consistent, we're going to have y is less than or equal to, so solve for y, you'll get negative 2/5 x plus 10. Alright, now those are ready to graph as lines. These guys are already good. This one says this way only, and this one says this way only. In other words, we only want the first quadrant. Okay, this one we got to draw a line on here, so I'm going to get a line going. So the y-intercept is 16, and I've got to go down 8 over 5. So from here to down 8 over 5. So I'm going to try to draw that on here as best I can. I think that's about right there. Okay, and the other line is going to be, let's see, starting at 10 and going down 2 over 5. I think that's through that same spot, coincidentally. This is an easier problem, like that. Okay, so now you want to think about where you're supposed to shade. And I'm not going to shade on here, it's just going to be too big of a problem. But we're supposed to be below both these lines. So is this area up here below both? No. This area below both. Now it's above both. This area? Ah, it's below that one, but not below this one. So I think it's only in here, and remember we're going this way and this way. It's this little region right in here, which are the answers that this bat company is going to be able to actually do for their situation. So part C down here says the company makes a profit of 17 for the wood ones and 29 for the polymer ones. So let's write down our profit functions. We're going to have 17x is 29y. Alright. And they want us to find the maximum amount of profit this company is going to make. So we've got a little chart here. So what are our vertices? So this one looks like it's 10, but are you really sure? You can't just assume those things. This one we know, right? We've got 0, 10 because that was the y-intercept. So let's put that one in. We've got 0, 10 right away. And we've got the origin. The origin's easy too. So we've got 0, 0. right away. But these two, even though it looks like we can kind of see them, you can't expect your graph to be perfect enough to have those. That's where you definitely have to either solve a system of equations to see where these cross, or go to your calculator. So I'm going to go to my calculator. I'll scoot this over for a second. Pull up my calculator. And let's have a look. So we're going to put our lines in. So I'm going to go to y equals. And our lines were, what do we have? We had negative 8/5 x plus 16. And then our second equation was negative 2/5 x plus 10. I'm going to hit zoom standard, and there's my graphs. Okay, so it looks like I can see both those intersections. Let's calculate this intersection first. So I'm going to go second, calculate intersection. So it says first curve. I'm going to scroll over here. Might take a second. There we go. That's on the left-hand side up there. I'm going to hit enter. Now on the other curve, I'm going to go on the right-hand side, something like that. And I'm going to guess right as close as I can be. So it looks like 5/8. It's another corner we need to check. All right, now this guy is not an intersection. It's actually a 0, isn't it? So let's find it. Looks like it's at 10. Let's double check. Second, calculate 0. And we're on the right curve. Let's go down here. So I'm going to say right there's good, and then right bound. Oh, it stopped at the edge. I better make my window go a little further in terms of x. Let's go to 20. Go and calculate that 0 over again. That's on the left. That's on the right. We think it's 10. It is 10. Alright, so we'll put the calculator away. So now we've got the vertexes that we needed to check. So our profit function, let's write that in up here. We had 17x plus 29y. Remember, this is just the profit that they're making for the bats too, so keep it in the back of your mind. Are they actually selling the wood bats for 17 bucks and the $29 bats are the polymers? No, I mean, they've got to charge more than that. This is just totally their profit, so think about that. Alright, so for this one, we've got 17 times 0 plus 29 times 10. I think that's easy to do in your head. That's just $290. 0 is going to be boring. They don't make any money because they didn't make any bets. 5/8. Don't always assume 0, 0 is going to be boring, though. It might not be. Make sure you check your function. I'm actually thinking about the function. Let's see, I'm going to use my calculator on that one. Let's see, second quit. We have 17 times 5 plus 29 times 8. So that's 317. And then we have 17 times 10 plus 0. It's going to be 170. So the maximum amount of profit this company can make in a week must be a really small company, because the maximum amount of profit they're going to make in a week is, get your units in there, $317. And they're going to make that profit by producing 5 of the wood bats. Units are already there. And 8 of the polymer bats. So basically, in terms of planning for the company, the most important part of information was the 5 wood bats and the 8 polymer bats. The fact that they only make $317 should tell you something about the difficulty of having a company like this. The only way you're going to make more money is by raising these 50 and 80 hours to much larger numbers. And to do that, you're going to have employ more people, and there's going to be all kinds of other constraining aspects to the problem. So we're kind of oversimplifying this a bit, but it does tell you that, like, this is how companies plan. This is how they decide how many trucks to make, how many bats to make, and all that kind of stuff. Okay, hope you found this useful. See you next time.